really going to start off by looking at a single Gaussian peak and learn quantitatively what information it gives us. But more importantly is what happens when you have two Gaussian peaks and they get closer and closer and closer together. Now, you don't want that to happen experimentally. You want to pull them apart. But we have to understand what happens as two peaks, which are nice and perfectly Gaussian, start to overlap with one another. So that's what we're going to be talking about here for quite a couple of days. So we're going to start off by looking at the impact of sigma. Sigma is the square root of the variance of the peak. It's the standard deviation of the peak. It's also the width of the peak. Sigma squared, the variance, is the square of the width of the peak. That's just the way the language works out. We're going to look at the impact of the number of tubes or the number of plates in the column or the Craig machine or whatever you want to call it. Then we're going to look at the area under a single Gaussian peak and understand how that area builds up as you move across a peak. Then we'll get into some basic issues related to resolution. Resolution means how well separated are the peaks, how well resolved are the peaks. We'll start with the definition. Then we'll move on to a very important equation which really helps, has a huge impact on understanding how to develop a chromatographic method, which is the general resolution equation, which I usually ascribe to Howard Purnell as the originator of this particular equation, so I might refer to it as the Purnell equation also. Then we'll start examining what happens to a pair of peaks as the resolution changes, as it gets worse and worse and worse, or as it gets better and better and better. And we'll look at pairs of peaks like 1-to-1 peaks, equal height peaks, then 2-to-1 peaks, and then more and more discrepancy in the peak heights, and see what happens. See how much resolution you need to get a decent separation. So that's most of what we're going to talk about for the next couple of days. So we have to start with the basic Gaussian peak. And this equation here, we basically derived this equation the other day by taking the limit of the Craig apparatus, taking the limit of the distribution, the binomial distribution, as the number of transfers gets really big. I'm giving the equation as a function of the volume of eluent that you put into the column. W is the total amount of a particular compound, say compound A, that's in a mixture. Sigma V is the standard deviation of the peak for compound A, and VR is the retention volume of the peak for A. Now, I've given this in terms of volume, but we could transform it into an equation as a function of time by relating volume to time if we know the flow rate. But that just means I rewrite the equation. It's no biggie. We're also going to look at things in terms of the number of tubes or plates on the column, and according to the plate model, that will work out to be N, which is the ratio, is the square of the ratio of the retention volume to the standard deviation of the peak in the same units, therefore in volume units. But I can look at N as any pair of numbers I want as long as they have the right units. So it can be volume, retention volume, over the standard deviation in volume units, or the retention time over the standard deviation in time units. In the old days, when we didn't have computers, we often measured the volume in inches of chart paper. As long as you use the same units, you can calculate n by this formula. So all I'm doing in the third equation is I'm substituting sigma v is equal to VR divided by the square root of n and plugging in. And that gives us this very useful formula. Okay, now I'm going to come back to this equation in a second, this last equation in a second. Let's look at a plot of the equation. Okay, here's a Gaussian peak. And we're going to talk about all of the characteristics of the Gaussian peak. Well, it turns out that the Gaussian peak is at an absolute maximum when V is equal to VR. See, if I set V equal to VR, I get 0, and so I have the exponential of minus 0, which is 1. Is the biggest number you can possibly get. Doesn't matter whether V is less than VR or bigger than VR, you're squaring that number. It's always a positive number. Always, always, always. So now if you take the exponential of minus a positive number, the exponential is always less than 0, which means the exponential function is less than 1. So the peak maximum is always at V equal to VR. Whoops. If I set V equal to VR, here's the coefficient in front of the exponential term, and this is the concentration of the peak at the maximum. Now, what does the equation tell us? It tells us that the more sample you squirt in, the higher the peak is, right? C max is proportional to W. It's inversely proportional to the retention volume, which means the later the peak comes out, the smaller it's going to be. It's also related to the square root of the number of plates on the column, where the n is in the numerator. So now, if you have two columns that are identical except one has more theoretical plates, n is also the number of theoretical plates, one has more plates than the other, the column that has more plates is going to give you a bigger peak. Okay, so let's look at this Gaussian peak now. This is an important little chart. It says that the area under the peak, if you were to start integrating the peak here at V minus VR equal to 3 sigma, and then stop integrating the peak over here, where V minus VR is again equal to 3 sigma, you would recover 99.7% of the maximum peak area. I don't know what the answer is if you go from -4 to +4 sigma, but it's closer to 100%. It's like 99.9 something percent. Okay? As you move in and you integrate from -2 to +2, you only get 95.5% of the total area. And then if you go from -1 to +1, you only get 68.3% of the peak area. So what do you think you should set for the integration limits on a peak to recover the peak? 1 sigma on either side? I don't think so. 2 sigmas? 95.5 is not so bad. Not so bad. But really, I think to talk about quantitation, you're looking at it at the 3 sigma limits. The 4 sigma limits, the difference from 100% is so small that within experimental random error, there's no. So So there's no point in making your integration window go from -4 sigma to +4 sigma. That's just a waste. And what you're doing when you do that is you're acquiring baseline noise. And you don't want to acquire baseline noise. Okay, fact number 1. Fact number 2. If you look at the shape of the curve, there is an inflection point at exactly 1 sigma unit before the peak maximum and exactly 1 sigma unit after the peak maximum. There's an inflection point there. Remember that. I just told you about that chart. Oh, I got it right. If we go 4 sigma, it's 99.99. Okay. See this quantity here, m equals 4 sigma. M is what's referred to as the baseline peak width. The baseline peak width. That isn't exactly what it is. In order to get M, what you do is you draw a tangent to each side of the curve where the tangent is tangent to the curve at each inflection point. So it's tangent here and it's tangent here. You take those tangent lines and you extrapolate them back until they penetrate the baseline. And what you'll find is that the one on the left penetrates the baseline at -2 sigma, exactly -2 sigma, and the one on the right penetrates the baseline at exactly +2 sigma. So if we're going from -2 sigma to +2 sigma, the width is obviously 4 sigma. This definition is very important because it plays into how we define resolution. So you need to know what M means. Okay, let's proceed onwards. Now let's look at the effect of sigma on the peak. So I'm keeping everything constant. I'm leaving the retention volume alone. I'm leaving the plate. I'm leaving the mass of sample I'm injecting alone. And all I'm doing is playing with sigma. And I'm going to take sigma from a value of 2.5 to 5 to 10. What do you see? Well, the obvious thing is the peak maximum comes down, right? Obvious thing to see is the peak gets wider. But the peak does not shift on the volume axis. It's the same. The peak doesn't move in that dimension. That is fixed by VR. The width of the peak and the height of the peak are impacted by sigma. Now, you're going to have to trust me here because eyeballs do not do good integrations. But these 3 peaks have identical areas. They're not similar. They are identical. Sigma has no influence on the peak, on the total peak area. In fact, VR has no influence on the peak area. The only thing that impacts the peak area is W, the amount of sample that you inject. Now, let's look at our first chromatogram. Suppose I say that all of my peaks have the same number of plates, N, 250, and I'm going to inject the same amount of each sample, and my detector responds the same to each sample. And I'm going to keep the peak separation, the VR, I'm going to keep that the same. but I'm going to simply increase VR. This is what your chromatogram is going to look like. The first peak, the earliest peak, is narrow and it's pretty high. There's the same amount in each peak. The areas are all the same. You have to trust me. The second peak is a little broader and it's not so high. And the third peak is broader yet and it's not so high. And this is reflecting and is broader. So as you move out, the peaks become less high and they get wider. And that is an immediate consequence of this Cmax equation, and when I manipulate that one algebraically, the n equation algebraically, it tells me that the sigma gets bigger and bigger as retention increases and increases. Okay, that's the next slide. I wanted to be here. This is an identical set of parameters for all the peaks, except I've made the number of theoretical plates twice as big. What do you see? This peak got bigger, it got narrower, but then we have the same trend. Wider and stumpier. If I increase the number of plates again, I almost have enough plates now so that even this is a semi-decent separation. And of course, the peaks are all higher than before and they're all narrower than before. Clearly, you want to get a lot of plates. More plates is good. More plates is good. Everything else remaining the same. But that's a proviso there, an important proviso. Everything else has to remain the same. So let me summarize a few of the things I've said already. There's an inflection point, 1 sigma unit on either side of the peak maximum, which means that the width of the chromatogram inflection point to inflection point is 2 sigmas. If I plug in to the Gauss equation, the volume equal to retention volume plus or minus sigma, what I'll find out is that the height of the curve at the inflection point is Cmax times exponential of -1/2. Exponential of -1/2 works out to be 0.606 something, 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 something. But 0.606 is certainly good enough for government work. Okay? Now, 0.606. Let's go back to the Gaussian peak. There's another quantity that we often use to measure the peak width, and that's the peak width at 1/2 the maximum peak height. So that's obtained by going exactly up to the 1/2 point on the left, 1/2 point on the right, and measuring the distance between those. That is obviously slightly below the inflection points, because the inflection points are at 0.606, whereas the peak width is at 1/2, which is more like there. So the peak width at the half height is a little wider than 2 sigma units. And we can actually derive work out an equation for that. And somehow or other I forgot to do it. But it works out to be 2.345 times the width of the peak. The derivation's in my notes. You should take a look at the derivation. It's not hard. It's just algebra, basically. So now we have to move on to a more important subject, and that's the area under the peak. So we have to integrate a function which is a Gaussian function, and that means that the argument of the exponential, it has the form minus x squared. It turns out that there is a perfectly well-behaved, well-known mathematical function that allows you to look up the numerical value of the integral of the Gaussian function. And this function is known as the error function, and it's always written as ERF. So the ERF of the number z can be actually any negative or positive number from minus infinity to plus infinity, doesn't matter. But the error function is usually defined as the integral from 0 to z, and it's always normalized with the factor 2 over root pi, and it's defined as the integral from 0 to z. So it's really the integral starting at the peak maximum, that's where z is equal to 0, and then out. Or it's the integral from 0 starting at the peak maximum and going backwards, going to minus z. But it's defined this way. There are tables of this function. Excel supports this function. So if you put in, say, ERF of 1 or 1.01673, Excel will spit out a number. If you put in ERF of 32, you'll get an overflow. It cannot handle a number bigger than 32. If you put in ERF of a negative number, Excel is too stupid to know what to do. Doesn't matter what the number is, if it's negative, it doesn't know what to do, but I'll show you what to do. I don't know why they did that. It's really not a hard fix. Okay, so now, let's suppose I ask the question, what is the area under the peak between any two arbitrary volumes, V1 and V2? Well, that's the integral from V1 to V2 of the concentration with respect to the volume, and that's going to work out to be, evidently, C max, the integral V1 to V2 of exponential minus V minus VR squared over 2 sigma V squared dV. The argument of the integral is obviously somehow related to the error function, because it's exponential minus something squared. So we have to put that into the form of the definition of the error function. So we're going to have to define the argument properly. But if you do the argument properly, you can calculate the area from the retention volume to any volume you want. This can be a volume after the peak maximum or a volume before the peak maximum. But if it's a volume before the peak maximum, you're going to have to deal with an error function of a negative number, which is perfectly well defined, except Excel doesn't know what to do. But it turns out to be quite simple. So the area from VR to V, if V is greater than VR, is W over 2. W over 2 means half of the amount injected times the error function of V minus VR over root 2 sigma V. And using this equation, we can generalize and work and determine the area between any V1 and any V2. We don't have to use VR. And that turns out to be, that's right. That turns out to be W over 2 ERF V2 minus VR over root 2 pi sigma V, ERF of VR minus V1 over root 2 pi sigma V. Now, V2 is taken as being bigger than VR, V1 is taken as being less than VR, so everything works out. The largest possible value of this is 1. The largest possible value of this is 1. 1 plus 1 is 2z. And there is a 2z. So the area from V1 well before the start of the peak, that's what makes that be as big as it can be, to V2 well after the peak maximum, that's what makes that be its maximum value 1, is W over 2 times 2. It's what you skewed in. That's good. Mass is conserved. Now we can plot that function. So if we start way over here, which is 4 sigma units before the peak maximum, the area is 0. I mean, it's like 0.00001 or something like that. In order to truly get to 0, theoretically, I have to go to an infinite distance before the peak starts. But as I approach the peak maximum, I start to acquire area more and more rapidly. When I get to the point where V is equal to VR, right there, I've acquired exactly half of the total peak area. And then as I sweep past the maximum in the peak, I acquire the rest of the peak. And if I go out here to 4 sigma units, I wind up at 99.99% of the peak area. So this does exactly what we expect. And certainly, if you're integrating a perfectly Gaussian peak, you're going to get half the peak area if you stop at the peak maximum. That makes sense, right? The Gaussian peak is symmetric about VR. So half of its area has to be before it, and half of it has to come after it. That's all there is to it. Here are some error function numbers for you to play with sometime if you want. Go to Excel and see what they put out. I quit after 2 decimals. You can get 6, 10, 16, 32 decimals, whatever you want. ERF of 0, well, the integral from 0 to 0, does it matter what the function is? It's 0. But as z gets bigger, the error function gets bigger, and gradually, ultimately, when you have an infinitely big z, you get exactly 1. This is the trick for dealing with the error function of negative numbers. The error function is an odd ODD function. Even functions, the function of x equals the function of minus x. Odd functions, the function of x equals minus the function of x. So it's an odd function. I don't know why they couldn't put that in Excel. I guess just to make chromatographers' lives miserable. Now the fun and game starts. That's really everything you could possibly want to know about one Gaussian peak. But what we really need to know about is pairs of Gaussian peaks. What happens when What I'm doing here in this slide is I've got two peaks. The two peaks are identical. They have the same width, and they have the same amount of material, the same W in them, but I've got different retention volumes. I'm going to leave one retention volume alone, and I'm going to change the other retention volume, and I'm going to make the other retention volume bigger and bigger and bigger. This is what you're going to see if the two retention volumes don't have much difference. You're going to see a single peak. It's going to come up, and it may even go flat, and then it'll go back down. You're not going to see a minimum between them if they're close enough together. Now, keeping everything the same, sigmas are the same, the amount is the same, I'm going to move the more retained peak out a little bit and make the separation a little better. You're then going to see this situation. You're going to have somewhat of a valley develop between them. You'll be able to see two peak maxima. The maxima may or may not be really, really close to where the maxima would be if they were perfectly well isolated peaks. If they were really narrow peaks, for instance. And then if I move the second peak further out again, I'm going to wind up in this situation. Now, I haven't moved it out so far yet, though, that I've gotten to a situation that we call baseline separation. Baseline separation occurs when the first peak, the two peaks are far enough apart so that the first peak comes all the way down and just touches the baseline before it goes back, before the second peak starts to pull the picture back up again. So that was the impact of how far apart the peaks are. I didn't change the sigma. In this slide, I'm doing the reverse. I'm going to leave the peaks alone in terms of their position and the amount injected, but I'm going to degrade the resolution by making the peaks wider and wider and wider. So we're going to start in this situation here. We got a really nice peak. The peaks are far enough apart, and each is narrow enough so that I get a nice little stretch of baseline between them. This is really what you're after when you're doing chromatography. You don't want a mile of baseline between them, because that's wasted time. But you definitely want to see baseline between your peaks. Assuredly, when you're quantifying the peaks by measuring the area underneath them and integrating them, you definitely want to get to baseline, if you possibly can. Now, if I make the peaks a little wider, well, actually a good bit wider, because that drop in height was pretty big. But if I make them wider, then I get to this situation where the valley doesn't get all the way down to baseline. And then if I go further and make them wider again, I have this very, very shallow valley. And if I made them wider, you wouldn't even see the valley. It'd come up, it'd sort of do a plateau, and then it would come back down. It'd only be one maximum. Okay, so considering the previous slide and this slide, what are the factors that influence the resolution of two peaks?
Peak width?
Yes, the individual peak width influences the resolution. What else influences the resolution?
Retention volume.
How far apart the peaks are, their retention volumes. Those are the only two things that influence the peak resolution. The amount of sample injected, at least for equal sized peaks, does not influence how well resolved peaks are. The absolute values of the retention volumes don't matter. It's the difference in the retention volumes or retention times or retention distances in TLC, which we still measure with rulers. Although there are automatic TLC scanners now. Okay, so how we define resolution had better reflect the difference in retention relative to the peak width. Now, this is here to remind you to read this paper. I don't think that's right. I think I screwed that up because I gave you my classic collection, not the essential collection. But look for the paper by Lloyd Snyder and J. Chrom Psi. It's two papers back to back in 1972. It's a classic. And it's going to cover what do peaks look like when they're not properly separated. All I'm going to be able to do today for you is give you the internationally accepted definition of resolution. Okay, this is IUPAC. So if it looks ugly, it's not my fault. But resolution, which is written either as a capital R and also as a R with a subscript S, is defined as the difference in the retention property of the better retained peak minus the lesser retained peak. Peak B is always more retained than peak A, divided by MA plus MB, where M is the baseline width of the peaks. And so MA is for sigma A and MB is for sigma B. They don't have to have the same sigma. The definition still works. Okay? This is the central idea of resolution. It's the difference in retention relative to the peak widths. Okay? Critical. This equation you memorize. All right. The quiz will appear on the, yes?
Shouldn't that be the average on the bottom?
Oh, damn. Thanks, Robert. It's 2 times the difference in the volumes, and Robert's entirely right, because that's the equivalent to dividing the bottom by 2, which is the average of 2. Thank you. I always do that. I guess I don't have it memorized. The quiz answer will appear in the Google folder today. And I'll probably make some additional problem assignments in the next chapter in the notes. And you've got to start reading the Snyder papers tonight, because the 2 of them taken together are pretty long. They're pretty long. And they're pretty detailed.